Today we're going to begin talking about something called hypothesis testing. This is one of the big key ideas from statistics. So in order to talk about hypothesis testing, we're going to first talk about the basics today in this video, and then in the future we'll get into more specifics about testing claims regarding proportions, means, and standard deviation or variance. So again, basic concepts is what we're looking for here. So a little bit of vocabulary to get us started. When we talk about a hypothesis in statistics, what we're talking about is a claim or a statement about a property of a population. When we talk about a hypothesis test, we're talking about a procedure for testing a claim about a property of a population. Sometimes hypothesis tests are called tests of significance. So let's take a look at an example to understand what we're doing here. So we want to know about the majority of consumers being comfortable with drone deliveries or not. So the claim made is that the majority of consumers are not comfortable with drone deliveries. So we ask 1,009 consumers if they're comfortable with having drones deliver their purchases, and 54%, or 545 of them, respond with no. So using P to denote the proportion of consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. The expression P greater than 0.5 is a symbolic form of the original claim. That was a lot of words, and it might not make a ton of sense yet, but let's break this out a little bit. So the big picture, we have a claim that the population proportion P is greater than 0.5. And among 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? That's what we want to know. So if we had a result from our sample that 506 people, or 50.1%, that's just barely more than half, so that would not be significantly high. If instead 1,006 people were not comfortable with it, or 99.7% of our sample, that's clearly significantly high when we're looking for greater than 0.5, greater than 50%. But what about this result of 545 people, or 54%, that we found? Is that significantly high? So the method of hypothesis testing allows us to answer that question. Is the value that we found in our sample significantly high or not? So using technology, it's easy to obtain hypothesis testing results. And we're going to take a look at some output from technology to see what that looks like. So here's 4 different technologies. StatDisk is a program, Minitab's a program, TI-8384 Plus is a calculator output, and StatCrunch is again a program. So here we can see we get these p-values along with some test statistic that's a z-value. So let's break that down a little bit and see what those things are. So if we look at these 4 screens, they're all displaying a test statistic of z is 2.55, which is rounded, and they all include a p-value of 0.005, which is also rounded. So we want to focus on understanding how the hypothesis testing procedure works and learn the associated technology, and then we're going to be able to make sense of these results from the technology. So, significance. Hypothesis tests are also called tests of significance, and that reason is because we're looking to see if sample results are significantly low or significantly high. So we've been talking about this idea of significantly low and high for basically the entirety of the course so far. But this chapter, when we're talking about hypothesis testing, it's going to formalize those concepts into some kind of procedure that we're going to be able to tell whether things are actually significantly high or low in a little bit more streamlined way than we've done so far. So when we're talking about hypotheses, we have something called a null hypothesis. So the null hypothesis we write as capital H with a subscript 0. This is a statement that the value of a population parameter is equal to some claimed value. Our alternative hypothesis, which we write with as an H with a subscript 1 or maybe an A, capital or lowercase, then that's a statement that the parameter has a value that is somehow different than the null hypothesis. So we could be looking for less than, we could be looking for greater than, we could be looking for not equal to. So this is fairly small type in here to get this all onto one slide, but here's our procedure for hypothesis tests. The first thing that we do is we identify the claim, like we did in that first example. Then we give the symbolic form. We also did that in the example. Then we want to identify null and alternative hypotheses. We have not done that yet. And then we're going to select a significance level. We're going to identify the test statistic. And then there's two different methods that we can use. One of them is called the p-value method, and another is called the critical value method. In both of these, we're going to find values and then make a decision. And finally, in all of this, we restate our decision in non-technical terms. Now, even though the steps are the same with the p-value method and the critical value method, how we do those things is going to be different. We'll be taking a look at both of those. Now, before we dive into those two methods that I mentioned, there's also something called the confidence interval method. Now, in making confidence interval, what we were doing was we had some confidence level that we were working with. And so when we were dealing with like a 99% confidence interval, then we had that alpha value of 0.01. And that is our significance level, all right? And similarly, with a 95% confidence level, then our significance level is the 0.5. So those alpha values that we were dealing with, those are our significance levels, all right? You'll notice that for the two-tailed test, that's what we were dealing with this confidence interval. If instead we were trying to look at simply greater than or less than instead of not equal to, then we would be in this deal of the one-tailed test. All right, so because a confidence interval estimate of a population parameter contains a likely value of that parameter, we can reject a claim that the population parameter has a value that's not included in that confidence interval. And we were doing something like that when we were talking about confidence intervals. So that part is not new. So now we can use the original claim to create a null hypothesis and an alternative hypothesis. We're going to walk through that process with these different things. And so again, we had come up with what the claim was, we had put it into our technical terms, and now we're going to create that null hypothesis and alternative hypothesis. So we're at step 3 here. So we want to consider these things. So remember, our null hypothesis has to be that the symbol express the parameter equals some fixed value, and the alternative hypothesis can be less than, greater than, or not equal to that same value. So it's one that doesn't claim an equality. So in our drone delivery, we can apply these things. We've already applied step 1. We said, hey, the majority are not comfortable or uncomfortable with drone delivery. And then we have our idea of our symbolic form. So the original claim that p is greater than 0.5 is false, or if it is, then that means that p is less than or equal to 0.5. So step 3, coming up with our null and alternative hypotheses. So we're going to identify our alternative hypothesis. So using the two symbolic expressions that we have, p is greater than 0.5 and p is less than or equal to 0.5, well, neither one of those is necessarily an equality. They're both inequalities. So we need to decide which one's going to be the alternative hypothesis. So the one that doesn't have the equal sign as a part of it, right? Less than or equal to has the equality as part of it. That one's going to be our alternative hypothesis. So our alternative hypothesis is going to be p is greater than 0.05. Now, for our alternative hypothesis, remember it has to have an equal sign with it. So we're going to take the equality part of less than or equal to and use the equals to part as our null hypothesis. So our null hypothesis is going to be p equals 0.5. So, significance level. We need to identify a significance level. That was step 4 of our process. Well, a significance level, alpha, like our confidence interval 1, yeah, for hypothesis test is the probability value used as the cutoff for determining whether the sample evidence constitutes significance evidence against the null hypothesis. By its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when it's true. Right? So, this is like the false negative deal. We reject it, but it's actually true. All right, so our significance level is going to be alpha equals the probability of rejecting our null hypothesis when it's actually true. Simple enough. So significance level alpha is the same alpha that we saw in our confidence interval alpha. All right. And we defined this idea of critical value there. So common choices for alpha, they remain what they were before. We have 0.05, 0.01, and 0.1. 0.05 is definitely the most common. So then we move on to step 5. Step 5 says identify the test statistic that is relevant to the test and determine its sampling distribution. So if we need to be in our t distribution, our chi-square distribution, whatever table we're in, we might also be in the normal table. All right. So here's a quick table to help you make that decision. So if we're dealing with proportions, then we want our normal table. If we're dealing with our mean, our population mean, then we either want our t table or our normal table, depending on whether our population standard deviation is known. And our standard deviation or variance, we need our chi-square table. Nothing has changed with this stuff from what it was for confidence intervals. So if you got this with confidence intervals, all of this stuff in the table, it's really summarizing what we had for confidence intervals. So going back to our example, we have that we're looking at our claim of p is greater than 0.5. And so we're going to use the normal distribution since we're looking at a proportion. And we have to double check that NP and NQ are both greater than or equal to 5, and they are. And so then we're ready to move on to step 6. Step 6 says find the value of the test statistic and the p-value or critical values. So we go and our test statistic, what is that? Well, that's the value that's used for making a decision about the null hypothesis. So it's found by converting the sample statistic to a score with the assumption that the null hypothesis is true. So here we have it. Right? We're going to go through, we find all of the stuff that we're dealing with here. We're going to be assuming our null hypothesis is true, so we'll assume p is 0.5. And we'll find a test statistic of z equals 2.55 using our normal distribution table. So now that we've found z is 2.55, we can take a look at what a critical region is. So the critical region is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. So in a two-tailed test, when our alternative hypothesis is not equal to, then we're dealing in our two-tailed test. We have a left-tailed test when our alternative hypothesis has a less than sign in it. And we are dealing in a right-tailed test when our alternative hypothesis has a greater than in it. So two methods to choose from. The first one was our p-value method. So in a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming the null hypothesis is true. So taking a look at our example, we look at the test statistic z equals 2.55, and with the normal distribution area to its right is 0.0054. All right, so it has a p-value of 0.0054. So when we were looking at our technology displays, it was showing 0.005 after rounding. That's where that came from. So here's a table telling us how to find p-values. So we start and we go in and we say, what type of test is it? Well, it can be a left-tailed test, it can be a right-tailed test, or the line going straight down isn't labeled, but that's for a two-tailed test. All right, so if it's a left-tailed test, then we go to the farthest left box to find out how we find our p-value. If it's a right-tailed test, we go to the farthest right green box. And if it's a two-tailed test, we have to answer one more question, and that is the test statistic to the right or the left of center? And depending on what it is, to the left or right, we have two different things that we need to do. These things fall into categories. So the left-tailed and right-tailed, they're the same, just one of them is looking to the right and one of them is looking to the left. And the two-tailed one, again, it's the same regardless of which side it's on, just one's looking to the left and one's looking to the right. So don't feel like you have to remember four things. Just remember that you have to, that left and right makes a difference, and then there's two things to remember. So some caution. Don't confuse a p-value with the parameter p. We're dealing capital P like probability and the statistic, the population parameter p, or our statistic p hat. So lots of p's going around, and when we're speaking it out loud, it's not a bad habit to talk about our capital P or lowercase p if we're not saying p-value. As long as we say p-value right away, you should know that that's capital P. So let's take a look at the critical value method. So in a hypothesis test, the critical values are the ones that separate the critical region, where we're going to reject the null hypothesis, from the values where we don't reject our null hypothesis. So in our drone delivery situation, our critical region is going to be the shaded one, the green one to the right. So if we have a significance level of 0.05, then we're looking for an area of 0.05 to the right. So we find that, and the critical value is going to be z equals 1.645. Right? So that critical value we need. So then we're going to make a decision whether we reject our null hypothesis or we fail to reject our null hypothesis. This is important. We never actually accept our null hypothesis, we just fail to reject it. That's the best we can do in that form. So rejecting the null hypothesis feels like a more direct, and it kind of is a more direct decision than this fail to reject option. So we're going to make our decision to either reject or fail to reject, and our decision criteria are going to be if our p-value is less than or equal to alpha, then we're going to reject our null hypothesis. This is for the p-value method. And if the p-value is greater than alpha, we're going to fail to reject it. So then we restate the decision using our simple and non-technical terms. So without using technical terms, all right, like ones that you could talk to your parents, tell your parents about this, or your friend or whoever who doesn't know anything about statistics, you need to use words that they're going to understand. So the way this could sound for us, for the drone delivery, is there's sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries. All right, no technical terms in there. All right, so wording that final conclusion, some tips there. So we usually indicate our support or lack thereof for our original idea. Right. So again, here's some ideas where the conditions, like what's happening technically, and the words that you might choose to describe that. Right. So again, this fail to reject. We used the term fail to reject because the term accept is misleading because it implies incorrectly that the null hypothesis has been proved. But we can't actually ever prove a null hypothesis. So we have to use this phrase fail to reject when we're talking about it. Again, multiple negatives here, fail to reject. That gets confusing for people. So like instead of saying things like there is not sufficient evidence to warrant rejection of the claim of no difference between 0.5 and the population proportion, we might instead say something like until stronger evidence is obtained, continue to assume that the population proportion is equal to 0.5. Right. So we try and simplify it in terms of English and not getting lots of double negatives, triple negatives running, but it's important that we avoid that misleading word accept as we go through that. Confidence interval estimates of a population parameter contain the likely values of that parameter, and we should therefore reject a claim that the population parameter has a value that is not included in the confidence interval. So when we're using confidence intervals, that's our deal. So that confidence interval test, it's actually equivalent to a confidence interval, So that confidence interval method, it's actually equivalent to a hypothesis test in the sense that they always lead to the same conclusion when we're talking about means and standard deviations or variances. But that's not the case with proportions. Now, error. So there's two types of error. There's type 1 error and type 2 error. Type 1 error is the mistake of rejecting the null hypothesis when it's actually true. That's that false negative situation, and that is our alpha value. So we say alpha is that. Type 2 error is the mistake of failing to reject the null hypothesis when it's actually false. Right? So that, in a way, is our false positive. All right, so we fail to reject, but it's actually false, and we use the symbol beta for that. So there's basically this table where there's 4 different possible outcomes. 2 of them we made the correct decision, 1 of them we have type 1 error occurring, and 1 of them we have type 2 error occurring. So this table is incredibly helpful to let you know which one's occurring. So if we're failing to reject our null hypothesis, the only type of error that could have happened is type 2 error, or we made a correct decision. And if we reject our null hypothesis, the only error that could occur is type 1 error. Otherwise, we've made a correct decision. So when we're describing types of error, right, so we want to consider this claim where we are looking again at this idea of increasing the likelihood of a baby girl, whether that's effective or not. So we want to describe how type 1 error and type 2 error could happen when our null hypothesis is 0.5 and our alternative hypothesis is that P is greater than 0.5. So type 1 error. A type 1 error is the mistake of rejecting a true null hypothesis. So in this case, we would say in reality P equals 0.5, but our sample evidence led us to conclude that P was greater than 0.5. That's a type 1 error. A type 2 error is where in reality P was greater than 0.5, but we failed to support that conclusion. So our sample evidence actually led us to not support this point, or P is greater than 0.5 situation. When we're talking about the power of a hypothesis, we find that by taking 1 and subtracting from it the probability of a type 2 error. So that's 1 minus beta. That's what we're talking about when we talk about the power of a hypothesis test. Right? And the value of power is computed by using the particular significance level and a particular value of the population parameter. That is an alternative to the value assumed true in the null hypothesis. It's a lot of words, but let's take a look at an example. So consider these preliminary results where we've got this XSort thing where we have 13 girls among 14 babies born, 2 couples using this XSort method. Right? So if we want to test the claim that girls are more likely, P is greater than 0.5 with the XSort method, we have the following null and alternative hypothesis. P equals 0.5 and P is greater than 0.5. So our significance level of 0.05, so in addition to all given test components, finding power requires that we select a particular value of P that is an alternative to the value assumed in the null hypothesis. So the null hypothesis says it's 0.5. So let's say instead P is actually 0.6. Or we're going to do this with P is actually 0.6, 0.7, 0.8, or 0.9. But we need some specific alternative value of P in order to determine power. So when we have the specific alternative, then we can find the probability of a type 2 error. Now we can do this by hand, but in this case, these results, we used Minitab. We used a statistical software to find them. So we find the probability of those type 2 errors, and we subtract them from 1, and those gives us the power of the test. Notice the specific alternative, as it increases, the power of the test also increases. So how we interpret this. So we see that the hypothesis test has a power of 0.18 or 18% of rejecting our null hypothesis when the population proportion is actually 0.6. That is, if the true population proportion is actually equal to 0.6, there's an 18% chance of making the correct conclusion of rejecting the false null hypothesis that P equals 0.5. That low power is not so good. Where if we bump this up, where we're looking at P is actually 0.7, now we have a 0.436 probability of rejecting. That's a little bit better. And again, if it's 0.8 or 0.9, then we have a much better chance of actually rejecting the false null hypothesis. So this is how this might play out. So we might have the trial designed, assumed that the 0.05 significance level, 153 randomly selected subjects would be needed to achieve 80% power to detect a reduction in the coronary heart disease rate from 0.5 to 0.4. So from that statement, we know that we have a significance level of 0.05 and the power of at least 0.8. Right. So we can take a look at that, and basically what happened is they found to have that idea, we required a minimum sample size of 153 for that to happen, and they used software to do that. We could potentially do it by hand though also. So that's it for our idea of basics around this hypothesis testing thing, and we'll look into specifics and computing a little more of this with means, with proportions, with standard deviations and variances in the lessons coming forward.